So when you solve the determinant of a minus lambda I equals 0 for lambda, what is that solving for? Eigenvalues.
Yes. You wouldn't say eigenvectors?
No, you'd say eigenvalues.
Remember the chapter.
In the equation AV equals lambda V, V is called a eigenvector. And then to find the determinant of a 2 by 2 matrix, yeah, you just do AD minus BC, so you would do 1 times 4 minus 2 times 3, negative 2. Okay, quick look at our schedule. We're talking about 3.2 today. Next week is a short week because spring break starts on Friday.
Friday?
Yeah. Yeah, we have Friday off and then the whole next week off.
Wow.
Yeah, nice, right? So next week's a short week, and on Wednesday, the last day before spring break, I'm going to give you take-home quiz 4. And it will be due when you come back on the Monday, the 28th, so you have a long time to do it. I actually might give it to you Monday. I mean, it'll still be due on Monday the 28th, but I think that you'll be able to do it after class on Monday if you want to get it done before you leave for break. Be up to you. Okay, so this is the same linear system we were studying last class. So let's just practice translating this to 2 equations, because I wrote it in matrix form, 2 different ways of writing this in matrix form. The bold y prime and the bold y mean x prime, y prime, and xy. So I wrote it both ways here. And when you translate this, you get 2 equations. X prime equals, you multiply your 2, 3 times your xy, take the dot product, and you get 2x plus 3y. And then y prime is 0, negative 4, dotted with xy, so you get negative 4y. The same system we were looking at last class. It had 2 straight line solutions through the origin. So I just gave them to you last class, and we verified that they were solutions. Then we plotted them in a direction field, and we said it looks like those 2 lie on straight lines, right? And I assured you that they did. Many of you didn't quite believe me, because it's really hard to tell when you look at a direction field, because it's so qualitative. Okay. But this is what the direction field looks like, and you've got a straight line solution here and here. And then we came up with a third solution that was a linear combination of those 2, and it kind of used them asymptotically to create that third solution. So today we're going to discuss how to find straight line solutions. So last class I gave them to you, and we said, well, that's great, because if you know 2 solutions, you can get the general solution by just taking a linear combination. So if we can find the 2 straight line solutions analytically, then we can find the general solution. All right, so we're going to go back a little bit. Think back to how to create a vector field for a system of ODEs. I had you do one little question on your test recently, like put in one little vector. So you just, for every point, you plug the values of the point into the x prime and y prime, and you get a vector. And it points in a direction, right? And that vector is actually tangent to a solution curve. So in the case of a straight line solution, think about what does a tangent to a straight line look like?
Straight line.
It's exactly on the line, right? Yeah. So in the case of a straight line solution through the origin, the tangent vectors, which are x prime, y primes, lie directly on the straight line solution. So that means that they are multiples of x, y. So x prime, y prime would be a multiple of x, y. So that means we're looking for vectors x, y, such that x prime, y prime is some random multiple of x, y. So x prime, y prime is lambda x, y, and that is the definition of an eigenvalue.
So if this relates back to the parameters k, for any given, system of ODEs, when we have a parameter k, that's the same thing as saying the eigenvalue for the system. So let me clarify. In the reading, it said that when we have k times v, for v, it's the same thing as saying lambda times v.
Sure. Yes. Lambda and k are both just arbitrary constants.
So, yeah, essentially they're both multiples.
Yeah, yep. Yep, we're calling it lambda because when we studied linear algebra, we used lambda when we studied that particular equation. When lambda is positive, you get vectors that point away from the origin, and when lambda is negative, you get vectors that point towards the origin. So in our example equation, we're looking for x prime y prime equals lambda y, right? But x prime y prime is given by that matrix equation, a times xy. So the lambda values that make that equation true are called eigenvalues. The associated vectors, x, y, are called eigenvectors. And so basically we need to be able to figure out lambda, and we need to figure out x, y. We need the eigenvalues and the eigenvectors in order to build the straight line solutions. A course in linear algebra, which most of you have had, or a thorough reading of section 3.2. So if you need a refresher, just really read it carefully. Reminds us that solving ay equals lambda y for lambda is done more easily by solving the determinant of a minus lambda I equals 0. Okay, so that's how you find eigenvalues. And that equation is called the characteristic polynomial. And finally, once you know the eigenvalues lambda, you solve for the eigenvectors by solving AV equals lambda V. All right, so we'll do an example because that was all pretty general. All right, same system. I want to find the eigenvalues. Okay, so to find the eigenvalues, we solve the determinant of a minus lambda I equals 0. And we solve that thing for lambda. What is A again?
Our coefficient matrix.
It's the coefficient matrix 2, 3, 0, negative 4.
I is
Okay.
the identity matrix.
I is the identity matrix, so I is 1, 0, 0, 1, which means lambda I is lambda 0, 0, lambda. So I could take the determinant of a minus lambda I. Okay, so this becomes the determinant of 2 minus lambda, 3, 0, negative 4 minus lambda. So that equals 0, and we'll solve it for lambda. The determinant of a 2 by 2 matrix, you just do diagonal AD minus BC. Yep, so this becomes 2 minus lambda times negative 4 minus lambda. That's your AD minus BC, which is 0. I'm just writing it out so that you don't forget that that's part of the formula. Okay. And then you solve this thing for lambda, and you get lambda equals 2 and negative 4. So I've got 2 eigenvalues. Okay, then I want to find the eigenvectors associated with each eigenvalue. All right, so let's see. Let's start with lambda equals 2. So for lambda equals 2, I want to solve ay equals lambda y, where av equals lambda v. Y and v are just names of the vectors. Okay. All right, so a is 2, 3, 0, negative 4 times some vector xy equals lambda, which is 2, times xy. I really need more space for this. Okay. So I just need to figure out any vector xy that will make that true. There's going to be infinite numbers of them. There'll be infinite number of vectors xy that make that true. So the easiest thing for me to do is to translate this to an equation that says 2x plus 3y. Right, I'm taking the dot product, multiplying the matrix times the vector. 2x plus 3y equals 2x. And then my other equation says negative 4y equals 2y. So we've got this system of equations. two unknowns. What kind of vector, what kind of x's and y's will make that true?
1 and 0.
If x is 1 and y is
Or just 0.
0.
That's
X
too
could,
easy.
x could actually be anything, right? As long as y is 0, both of those equations will be true. So my y here, the easiest eigenvector to choose would be 1, 0. Anything 0, right?
What about 0, 0?
No, an eigenvector has to be non-zero. That's part of the definition of an eigenvector.
What was that? My bad. I'm sorry. That was crazy.
All right, so that's for lambda equals 2. We now have an eigenvector that goes with lambda equals 2. Or, right, any number 0. Right, you can pick anything.
A 0, right?
Yeah. So I typically just pick the easiest one. Simplest. All right, let's go to another page to do the lambda equals negative 4.
The number of eigenvectors?
Yes. Okay, so for lambda equals negative 4, again, we want to solve ay equals lambda y. And a is 2, 3, 0, negative 4. Y is what I don't know. It's some unknown vector xy. That's the eigenvector I'm looking for. So I typically just translate this to a system of equations. So I have 2x plus 3y equals negative 4x. That's my first component on the left equals my first component on the right. Second component on the left gives me negative 4y. The second component on the right is negative 4y. What kinds of vectors would make that true?
Negative 2, 1.
Negative 2, 0.
Yeah, negative 2, 0 definitely works.
Yeah, so this second equation gives us no information whatsoever, right? It says y could be anything. So let's look at this first equation, and if I solve it, so I would get like 6x equals negative 3y, or 2x equals negative y, right? Something like that. So any x and y that makes that true will be good. Okay, so the second equation tells me nothing, because any y would make that true. So I go to my first equation, and if I made x 1, y would be negative 2. Right? And again, there are infinite vectors that would make that equation true. So you could also pick negative 1, 2. Something like that. All right, so there's my second eigenvector. All right, so we now know the eigenvectors. I want to graph the straight line solution curves that appear on the vector field and mark the arrows on each line showing the direction of the solution. So this is x, y, my direction field. And my straight line solutions are the eigenvectors. So I have 1, 0 is one of them. So this is one of my straight lines, the line that goes through the origin and 1, 0. Now, should I point my direction arrows towards the origin or away?
Depends which side you're on.
Away.
Away from the origin, sorry.
Away from the origin, because lambda is positive. When lambda is positive, these point away. Okay, so there's one of my straight line solutions. The other one, the eigenvector was 1, negative 2. So I plot the line that goes through the origin and 1, negative 2. So something like this.
So you know these go through the origin, so you don't have to plot 2.
Right. Yeah.
Points towards.
And it points towards because what was lambda for that guy? It's negative 4. So now it points towards the origin.
Is this an established pattern, like this is going to happen for pretty much all sorts of values?
Yeah.
So like when you get like you have one set of solutions, the other set of solutions, you know, like one eigenvalue and the next eigenvalue, one's always going to point away from the origin.
Oh, that will happen a lot, but it's not always. Yeah, that is one particular pattern that results in one particular kind of phase portrait. It's the only kind we're studying today. Yeah. So this pink one, remember this corresponded to lambda equals 2. Sometimes we label these just to sort of keep this straight, to remind ourselves why the arrows are going where they're going. All right, so here's a little present for you. I'm just going to tell you that for each eigenvalue and an associated eigenvector, you can produce an analytic solution to your differential equation that has the form e to the lambda t v. It solves your differential equations. So I want to write down two particular solutions to my system of ODEs that we've been working with here. So y, that's a bold y, which means xy, right, equals e to the lambda t, and I'm using 2 as my lambda. And then v was 1, 0.
That can be any of your eigenvectors?
Any of your eigenvectors will work. Yep. And then when you have v is your eigenvector. Yep. Yep. E is v is an eigenvector. So then this could be simplified to e to the 2t 0, right? It's like distributing. Multiply that e to the 2t times both components. So that's a solution. That's an x of t, y of t. So let's call this x1, y1. And then I'll have another solution, x2, y2, which is e to the negative 4t times 1, negative 2 was my other eigenvector. I went with negative 4. Multiply that out, and I get e to the negative 4t. And negative 2e to the negative 4t. That's another solution, an x and a y that makes the differential equation, the system of differential equations, true. I could ask you to verify that they were solutions, but those are the two solutions that I just handed you on Wednesday, and I already had you verify that they were solutions.
Well, it'd be really simple to check, see if they are.
Yeah, it would be really quick if you wanted to. Yeah, or you could just flip back 5 pages and see that you did it already.
What determines the number of eigenvalues? With the 2 by 2 is always going to be 2?
Yeah, with a 2 by 2, with a 2 by 2 matrix, you could have 0, 1, or 2.
And 3 by 3, you have 0, 1, 2, 3?
Because, yeah. Think about when you have a 2 by 2 matrix and you're trying to find eigenvalues, you're solving the determinant of a minus lambda I equals 0, and that will always be a quadratic equation, and quadratic equations always have 0, 1, or 2 solutions. Yeah.
So are we going to see 3 by 3 or any other size n by n matrix?
I don't think so. No.
Because then we'd have to use the diagonal of the solution.
Yeah, there'd be the calculations would be way harder. All right, so this is really exciting. We can analytically create two solutions, right? As long as we have two eigenvalues, yeah, we can analytically create two solutions to a system of equations by finding the eigenvalues and the associated eigenvectors. Okay. And that's good because last class, or 2 classes ago, we realized that all we need are two particular solutions, linearly independent solutions, and you take a linear combination of them and you have the general solution. So now I've given you a systematic way of creating two solutions. Then just take a linear combination and you've got them, the general solution. So let's just write down the general solution since we can. So my general solution xy, x of t, y of t, is going to be a linear combination of my two particular solutions I just found. So it would be k1 e to the 2t 0 plus k2 e to the negative 4t, negative 2, e to the negative 4t. And then if you had initial conditions for x and y, you could solve for k1 and k2 and get a particular solution.
So when you could have chosen any eigenvector, you also should have any k value to cancel out pretty much. Without the whole thing pretty much scale. You can scale those vectors pretty much, right?
The eigenvectors could be scaled, absolutely. Yeah.
Yeah.
So I could have used 2, negative 4 right here, right? I could have used 2, negative 4. If I used 2, negative 4 right there, I would end up with a different k value when I solve an initial value problem. But once you multiply that k value times the vector that you used, you and somebody else will come up with the same answer. Does that make sense?
It seems counterintuitive. It does.
Once you do it, you'll see that it works. It's hard to talk abstractly about like long strings of what's going to happen when you do algebra. All right, so that is how you find straight line solutions and general solutions to a system. So you're going to do some on your own now.